All right, so today I would like for us to finish off our notes for 2.3 by talking about a couple of different things, one being the molar enthalpy of combustion and the other one being the molar enthalpy of formation. And so hopefully these will go pretty fast. Molar enthalpy of combustion is very similar to what we've talked about with the molar enthalpies of or solidification. By definition, this is simply the amount of energy released when 1 mole of a substance undergoes a complete reaction with O2. And amount of energy being released denotes that delta H is going to be negative, which makes sense for combustion. And one thing I wanted to mention before we go on much further is that this is going to be done at standard conditions of a reaction. And to denote that, sometimes this delta H gets a little, almost like a degree sign. And that's just indicating that this is happening at standard conditions. So standard temperature, standard pressure. And that's all we're going to deal with in this class anyway. So if you see that little degree sign, that's just talking about the standard conditions are being upheld there. So nothing weird going on. So the molar enthalpy of combustion, you have the table in your reference sheets that give you some molar enthalpies of combustion. And that's per mole. That's a kilojoules per mole kind of deal. And what's interesting about that is in your bomb calorimeter that we learned about with Q equals MC delta T, what we can do is predict if something is going to be combusted in this bomb chamber right here. Oops, I use my highlighter. If something's going to be combusted in that bomb chamber right there, we know it's going to be releasing energy into the water. And then for the water, we can use Q equals MC delta T. And what we can do, and this is how all those molar heats of combustion or enthalpies of combustion are found. You can work backwards based on that to figure out how much energy was released by the combustion inside the bomb. And so I would like to do one of these problems with you. And it looks like this. Suppose 40.9 grams of methane completely combusts in a bomb calorimeter. If the calorimeter contains 500 grams of water at 20 degrees Celsius, what will the final temperature of the water be? So what we're going to do is we're going to use our delta H enthalpy of combustion, and we are going to figure out for methane how much, and so sometimes you see a little comb down there for combustion, maybe your standard conditions. We've got our 40.9 grams, and we know that for methane, CH4, it's going to take 16.0, that's CH4, so that would be 16.05 grams per mole. And then all we need to know is for every 1 mole of methane combusted, how much energy is it going to release? So that is on your reference sheet. I'm looking at your reference sheet right now, and the molar heat of combustion, molar enthalpy of combustion for methane, CH4 is, delta H is negative 891. So all we have to do now is calculate what that comes out to be. So multiplying all those values together, I get that 2,270 kilojoules of energy are released. Just as an FYI, when I plug this into my Q equals MC delta T for water later, that C is going to be in joules per gram degree Celsius. So I'm going to need to make these units match before I can get a real answer. So let's go ahead and figure that out. So for my water, I've got 500 grams of water. I know absorbing, that is that It's going to be absorbing, so it's positive, 2,270 kilojoules. Its mass is 500 grams. Its C is 4.184 joules per gram degree Celsius. And what we want is the final temperature, so the change from 20 degrees. So what I'm going to do is I need to change one of these two numbers. So I guess I'm just going to take kilojoules, and there's 1,000 joules in 1 kilojoule. So I'm going to multiply this number by 1,000, which just means I'm going to have that many joules. And so solving for delta T, let's see what we find. So I just get this absolutely huge change in temperature, 1,090 degrees Celsius. So I'm going to add that to the 20 degrees it started at. And so the final temperature of my water should be 1,110 degrees Celsius, which means this water is going to be completely vaporized. So that's not entirely true because we've got some delta H of vaporization to deal with, but apparently I should have picked like 5,000 grams for my water or something like that. So anyways, that's the basic steps you would go through, and you're going to try a few of those today, so I wanted you to definitely see that. I'm going to stop that video right here just so it doesn't get too long for YouTube, and then I'm going to continue on with part 2.